Okay, so hello everyone, and welcome to this webinar about Picterra versus traditional machine learning for geospatial data. So first we'll start by presenting ourselves. So I will let Stefan go first. Okay, so meanwhile, so I'm Julien Rabaté. I'm the lead software engineer at Picterra, managing the engineering team. And I have a background in software engineering and machine learning. And I'm joined by Stefan, who's the co-host and is on the DevOps team at Picterra, so managing all of our infrastructure. And he will talk in a second part on how we can basically bring the model that you build on the platform on Picterra at large scale.
Yep, and I'm here. Zoom unmuting issues. Happy to hear.
Nice. Okay, so let's see a bit what's on our plate today. So first, we'll talk a little bit about Picterra and what we provide as a product. Then the main topic is really how we compare and what are the advantages of using Picterra if you compare it to a traditional machine learning workflow that we see in geospatial company. Then we'll have a demo and showcase some examples from customers, also showing how you can bring the model that you build on Picterra at scale. And finally, at the end, we'll have a question and answer session. So you can write the session on the chat while we are talking. And at the end of the webinar, we'll take a few questions that we will answer live. So Picterra, we are a Swiss company based in Lausanne, in Switzerland, in the French-speaking part. Currently, we are 17 people in the team, and we are 5 years old, and already working with quite some big names in various industries that you can see at the bottom, and we have more than this. So what we really do at Picterra is we basically provide a software as a service. So it's a piece of software that you can access with a web browser, and what we allow our customer to do is basically train machine learning model on geospatial imagery data. So our users, they will have some data coming from plane, satellite, or drone, some imagery data that they want to analyze to extract some insights from. And what Picterra allows them to do is to train a machine learning model in a very easy and intuitive way to extract specific objects that's specific to whatever each customer wants to do. And then from this machine learning model that you can train on Picterra, you can then apply it at scale and get results in the form of reports, dashboards, or export it into GIS files for use in ArcGIS, for example. So just to make it a bit concrete, the platform, as I said, it's a SaaS platform that you can access with a web browser. So it looks like this basically. And you can upload images to it, and you can create your training data and then create reports on the platform. So before going into the demo and showing a bit how we changed the traditional machine learning lifecycle workflow, I wanted to give a bit of an overview of what I'm talking about. So if you look at the traditional machine learning project in, say, a big geospatial company, usually it will go through a number of steps. And so you start on the left and hopefully you end on the right. So I will quickly walk through the steps and explain a bit who's involved in each step. And then we can see how Picterra integrates in all of these steps. So the first step usually is just like organizing the data. So you get some imagery. Maybe you have a massive amount of imagery. If you're in the geospatial domain, you can easily have terabytes of imagery sitting on a hard drive that you want to use for a machine learning project. So already there, sharing this imagery with colleagues can be complicated. So usually, if you start a machine learning project, the data scientist will be involved with the GIS person to somehow make this data available for the project and for the team that will be involved in the project. The second step, if you want to use machine learning to detect some objects in your imagery, is to label the data. So you need some labeled data, some annotation to train the machine learning model. So machine learning, the model is really learning from the example that you give, and so you give this data labeling stage. That's usually quite expensive because you need someone to coordinate an annotation team. You also need to train the annotation team to make sure that they follow common rules to annotate the data, and you need to make the data available for the annotation team. Once you're past this stage, usually you hand it over to the data science team to build and develop the model. So develop the model means basically they will need to choose typically a deep learning model architecture, a backbone. They will need to get maybe some GPU machines from the IT department to be able to train this model on all of the imagery that you have labeled. And this can be super time consuming because you need to iterate. The first architecture that you choose might not be the correct one. You will have issues during the training, like managing memories, managing GPUs and stuff like this. And so really the whole develop and train the model parts are usually very time consuming, and this is where a lot of machine learning projects in the industry actually fail because they just run out of budget or run out of time in these two phases. And I will come back to this in a minute. So now hopefully you manage to have the data science team train a good model for the object you want to detect. Now you want to make it available to the rest of the company, to another business unit or to a client. And usually what will happen is the data science team will need to package the model and give it to a software engineering or DevOps team to make it available and deploy it on a server, for example. Maybe they will also need the software engineering team to develop a UI or an API to give access to the model. And this is a very complicated stage because there is a transition between the data science team and the DevOps team. And so there is miscommunication, not everything is well documented and so on. So this is another phase that's usually very painful and that can also lead to project failure. Afterwards, when you have the model running in production, you usually want to review the results that you get. So you will need some collaboration between the data science team and some GIS team closer to the business that can do this quality control phase. You will also need to maintain the model. So typically there will be bugs in production that you need to fix. It's not working on a specific image for some reason. So you will need a bit of maintenance. And at the end of the project, or once you get the first set of results, you usually want to visualize the results and to share them with coworkers or clients to show basically the results of your work. So now if everything goes well, and usually it doesn't, but if everything goes well, you will want to replicate this whole life cycle to a new type of objects. So you detected cars and now you're, okay, can we detect different type of cars? And there you have to start again from scratch. Now, if you look in the industry, we see that about 90% of data science projects, they never make it into production. And this is, I mean, if you think about it, this is massive. So it means there is a lot of wasted time in data science team training models that are actually never useful. And this is very often just because managing machine learning projects is very complicated and it can fail at all of these stages. And so usually these projects, they get cut because they run out of time or budget. And the company is saying, okay, we failed to deliver this, let's move on to other things. So what we bring with Picterra is basically we allow you to save on every step in the process. And the way we do this is because the platform, so our SaaS platform, it basically covers the whole life cycle. So on one side, you have the training part. So labeling your data, organizing new data, you can upload your imagery to the platform. You can super easily annotate your data and collaborate on annotating the data. So basically build your data set. And then you can train a machine learning model automatically. And once you have trained it, you can move on to the deploying to production part where you take the trained model and you can very easily, with a single click, apply it at scale on your whole library of images. So now what I want to show you is basically how training a machine learning model on Picterra works. And so I'm gonna go to the platform. So this is my account on the platform. I am in my detector library. which is one like the training side of the platform. And I will show you how I can create a new detector to detect bolts on train tracks. So the imagery that I'm going to share with you to show you here is from a client. It's a company called Plowman Craven, and they were nice enough to let us use this imagery as a sample in this webinar. So this imagery is very high resolution drone imagery, as you can tell. So it's sub-centimeter imagery, super nice, very nicely georeferenced, all of this. So very high quality drone imagery. And the goal here of what they are trying to do is basically to do inspection. So you want to inspect the railway tracks for anything that could be missing. So I will show you how you could build a detector to detect bolts. So the way to do this is first you define a training area on the image. So it's the yellow area. And here, this is basically the area where I have to annotate all of the example of objects that I want to detect. So in this yellow area, I will just outline all of the bolts that I'm seeing. I can actually easily copy paste that annotation to outline all of the bolts. And this is the way you build basically your training data set for your machine learning model. You can obviously do this on multiple images. You can do multiple of this training area. I'm gonna show you only one just to make the demo quick. But you can, the example that we will show later, they are all using like tens or hundreds of this training area. You can also do an accuracy area, which is a way to measure the accuracy of the model. So typically in a machine learning project, you split the data into train and test. And the test data set is not used during training to train the model, but it's only used to evaluate it. So it's a way to get an accuracy to kind of measure how well the model will generalize to other condition, to another part of the image or to other images. So here in the accuracy area, again, I'm outlining all of the bolts, but this data will not be used to train the model. It's only used to evaluate the model after I train it. And we'll see this after the training. And then the last kind of area you can do on the platform is a testing area. It's really, the testing area is a way to preview the results of the detector. So after I click train, the detector will detect all of the bolts in this red testing area. And it's a way for me to visually kind of assess where the model is doing good and where it's missing some detections maybe. So here I will click on train now. So what's happening now is there is basically on our infrastructure, there is a GPU machine that's automatically allocated to you. And it will train a deep learning model. So we are using it's a CNN model for the one who knows. That's trained fully automatically based on the training data that I just created. And it will be available in a few minutes, and we'll come back to the training at the end of the webinar to see what kind of results we got after the training. So the training, it can take anywhere between 10 minutes if let's say the data set is small, but on larger data set, we see training that can take a few hours, let's say. So obviously the more data you have, the more you benefit from having a longer training for the model to become better. So while it's training, I want to show you the kind of end results that you can get from these detections. So this is the report again that we built that the Plowman Craven, so the company owning the data, we built for them to show basically detection of change. So what's happening here is we have two images that were taken with a few months of interval. And so on the left side, you have one image. On the right side, you have another image. And if I slide the green vertical bar, you can see that it's changing between the two images. So it's a way to really detect changes between the two images. In this case, we detected two types of objects, so bolts and pandrol clips, which are holding the rail to the sleepers. And then we have some automated alerts when there is basically a mismatch between the detection on the first image and the detection on the second image. So if you look at this one, actually, it's interesting because you can see, if I remove the highlight of the detection, that there is the whole clip that is missing in the second image. It's here in the first one, but it's missing in the second image. So that's a way to really detect this kind of defects. On this same image, I want to show you another defect that's very interesting to look at a bit lower here. And this one is interesting because it's something that would be very difficult to spot if you were just walking the track, which is the way they currently do the inspection. So you have someone walking the track and seeing if anything is missing. And here you can see we have an alert, but the clip is still there on the rail, but it's getting a bit loose basically. So you can see that it's slightly moving. And this is very interesting because it opens the door to being a bit proactive in the maintenance and detect possible safety issues before they actually happen. So you can take actions a bit earlier and then be more proactive and therefore diminish the risk to have a massive safety issue. Okay, let me go back to the slide, sorry. Before handing it over to Stefan, I want to talk about another use case from a company called Civis or Marvich, and I think they are actually listening to the webinar. So thanks to them for letting us talk about their use case here. So basically, it's a company. They are building a dashboard in the forestry monitoring and management sector. So the end client is a forestry company. And they are using very high resolution drone data to basically track the growth of trees. And they start very early in the growth by taking very high resolution drone data. And then the detection that they get out of Picterra are integrated into a dashboard that they make available to their end clients. And so this is an example also where they are using some of our integration with ArcGIS to automate, like to make some parts of the workflow more efficient. So now if you look a bit at what their detector looks like, it's very interesting because this is some of the detection that they get. And you will see when you remove the detection that like you have no clue what it's detecting. I mean, from this image, you have no way to see visually what is the detector looking at. So if you zoom in a bit in the image on the detection, you will see that it's actually detecting some very small green patches that are really the beginning of the sapling starting to grow. So this is a very beginning of the growth phase of a tree. And again, if I remove the detection, this is the kind of object that the detector is looking at. I think what's very interesting here is that thanks to this very high resolution drone data, you can count this object at a massive scale and basically do something that would be humanly impossible to do if you had to do it manually. Because you can imagine going through these images manually would take a crazy amount of time. And so in their case, they have been using Picterra for a few years now. And I think they processed more than 4 terabytes of data through the platform last time we looked. So it's really a good example of how you can start training a detector on Picterra and then get it automatically in production for free, basically. So to conclude a bit the training part, of this webinar, what we like to say is if you can see it with the eye, we can probably detect it. So I leave the probably because I'm an engineer, so I'm always a bit cautious. So the marketing department will not like the probably, but I mean, usually if you can see it, we can detect it. The last thing I wanted to mention before handing it over to Stefan is some of the things that we are working on to make the machine learning experience on Picterra even better, is what we call experiment workbench. And you can think of it as basically a way for our users without data science knowledge to do some of the things that the data scientist would do in a traditional machine learning project. So we are looking at doing things like automatic architecture search to find the best model for your use case. We are also looking at ways to do recommendation on your data set to basically tell you which area of the image you should annotate or which image that you run the detector on would really help improve the detector for further use. And also we are opening up more parameters for users. So stuff like backbone, loss, batch size, the typical parameters you have in deep learning. Yeah, so now I will hand it over to Stefan, who will walk you through how you can take the simple model data train and basically apply it at crazy scale.
Yeah, thanks a lot, Julia. Very interesting. Especially excited about the experiment workbench stuff that we're going to roll out soon. So yeah, so I'm handling more the infrastructure part of things. So making sure that everything runs smoothly and then everything runs at scale. And here, for the next couple of minutes, I'm going to talk to you about the various challenges that you might face when trying to pull your models in and push them into production, and how Picterra can essentially help you solve these issues. So going into production, you might face some concurrency, scale, update, and uptime issues. I'll quickly just go over these. So what I mean by concurrency is the step you take when you go from 1 to n and all the fun problems that come with it. For instance, you might start to have multiple users that will need to use your model at once if you want to run it at a company scale. And you probably don't want to pass your laptop around, right? So you'll at some point need a dedicated machine for that, and probably some sort of job queue to automate the processing of all the job that all your users are going to send to you. Because even though you might be fine just running a script that runs that predicts on a batch of images, maybe at some point you'll have multiple batches of images coming up, and you need a sort of automated way to process all that. So you might need also more machines because you want to increase the parallel capabilities of what you can do. So you'll likely turn to a cloud provider for that. And so you soon realize that these machines are definitely not cheap, far from that. So you need to remember to turn them on when you need them, off when you don't need them anymore. And this raises all kind of fun issues, like especially for large enterprises that span multiple time zones, right? You maybe don't want to wake up at 4 a.m. to turn some machines on and off because some job starts or just finished. Another issue that you might face is scale. So a model, when you prepare it, let's say, it runs well in a controlled environment with images of a given size. But at some point, what if you want to feed it bigger images? At some point, you'll have to sort of scale up and size up your machines. But even the cloud has its limits. You can just give 1 terabyte of images to a GPU and expect it to eat it without issues, right? So you need to figure out some smart ways to process bigger and bigger images. A third issue you might face is updates and iteration. So let's say you improve your model by a couple of points. Say you improve your accuracy by a couple of points. You'll want to deploy that to your machines on the cloud. Do you just copy paste the model to each machine? Do you take them offline and copy paste the model over the internet? All that traffic between your laptop and the cloud is costly, definitely not free. So yeah, as time goes on, you'll probably want to keep that iteration loop as frictionless and transparent as possible. And that can be also a bit challenging to do. And lastly, you might want to control your services uptime. And what I mean by uptime is the time during which your service is available. It's opposed, obviously, to downtime during which the service is not available. And you'll obviously want to keep that as low as possible. So as coworkers start to rely on you for their daily jobs, you'll want to minimize all the disruptions. And plus, things are not entirely in your control. So a rat could bite some cable in the Netherlands and all your service goes down. It's out of your control, of course, but it kind of becomes your problem at some point. So you'll need to figure out a way to do this, to tackle these problems. Most online services provide a measure of their uptime, information and maintenance windows, a level of support, and they can figure out how to handle outages like this. And this is kind of the things that, all of these is like concurrency, scale, update at time. All of these challenges are not insurmountable. They're all solvable, of course, but they might require a lot of work and some new full-time positions that are dedicated just for that. As Julien mentioned, DevOps engineering, software engineering, people that are maybe outside of your area of expertise, let's say, and that you will need to hire to handle all of that additional work that you want to do. And that's part of the offering at Picterra. It's handling all of this on your behalf, essentially through our platform. So here's how we do this. Concurrency. So we compute metrics continuously that evaluate the workload that needs to be processed. And we have a job queue, all the jobs that arrive, then there, and we evaluate how much work there is to do. As soon as certain thresholds are reached, we spawn up new machines to handle that workload. And as soon as these thresholds are not reached anymore, we turn the machines off. So this helps us keep the costs low and also absorb large amounts of work. The way we handle scale is whenever large images arrive, we split them into smaller cells. I'll show you some examples of these cells later in the slides. So we split the image into smaller cells and then queue all of these jobs in our job queue. This increases, of course, the workload. This increases our metrics. Our cloud spawns new machines, new GPUs. They start eating up all these jobs. And also one cool thing that we handle is our cluster. So all our machines are spanning multiple regions. So we're not locked into a single data center. This means that because GPUs are a bit like in these times of everybody's doing ML, GPUs are sort of a scarce resource in data centers. If multiple people want to, from like different cloud users want to run stuff on GPUs, they might fight for these GPUs. So if some data center has no more GPUs available, we can still like steal some from the data center next door. And the update thing, we host weights on the shared storage, Google's Blob Store, which is directly accessible to all the workers, and it's also hosted directly on the cloud. So whenever you train a detector, this directly updates the weights on that Blob Store, and it transparently updates the detector for everyone that uses it. So there's no copy pasting involved, no downtime. All of that is transparent and seamless. So this helps keep the train, detect, iteration loop pretty frictionless. And finally, a quick mention of uptime. So maintaining all of this infrastructure that you might start to have is a lot of work, and keeping it up 99.9% of the time requires careful monitoring, alerting, load balancing, deployment strategies, backups, security management, all of that fun stuff, which really benefits a lot from being centralized in a single place for users, because 10 companies might each on their own handle this, alerting, load balancing, and all that. But it's something that really benefits a lot from being centralized. It's less work duplicated, so it's just a lot of less wasted effort, let's say, to do this in a central platform. Now I can go into sort of a theoretical example of how we scale when large jobs arrive. So here the blue line is the number of jobs on our work queue, and the red line is the number of machines that we have in our cluster. So here at time 1, we can, let's say we have a job that arrives, a worker picks it up and start to split it into cells. And at time 2, we can see that we've enqueued a lot of new jobs. So the work queue is becoming crowded. Our metrics update and detect that. We spot up new machines. You can see the red line moving up to a certain threshold that we've set. And slowly just crunching all of these jobs and eating them. At some point, there is no more jobs or fewer jobs than required. And we can start to scale down our machines and scale down our cluster. So this sort of spiky curves is the kind of things that we see from a DevOps perspective, and I'll show you some graphs of that later on. So all of this is all of these spikes here in the graphs are the platform breathing in and breathing out and expanding and shrinking as jobs are queued. Here's like a couple of cells that we have. So this is 300 square kilometers at 10 centimeter. It's from Hayward, which is a city in California. This represents 31,000 million pixels, so 31 billion pixels. So a lot of pixels, which we've split into 22 cells. Each of our cell is 900 million pixels. That's roughly the area of Zurich, if I remember correctly. And you can see that there is a tiny red arrow here, and this corresponds to this area here. So you can see it's pretty detailed. We're detecting in this case solar panels. But yeah, again, as Julien said before, going through all of that imagery manually would just take a lifetime, and you need somewhat automated way to do this. So going back to the previous slide, here's what the scaling looks like from DevOps perspective. So sort of how I see things. So you can see for the GPU jobs graph, the left part of it has a big spike, and that's when a user enqueued a lot of jobs, a lot of new jobs that require new GPUs. We can see that at that point, we've spun up new GPUs. We can see the GPU memory increasing, and also just the raw memory increasing as well. And you can see all of these spike patterns. That's whenever some user is enqueuing a lot of prediction jobs. And you can see this happening multiple times over a couple of days here. And finally, here are a couple of numbers. Just wanted to throw them out. Our platform has 99% of uptime, which means 10 minutes of weekly downtime, which usually happens on Mondays when we're doing all of maintenance work and releasing our weekly releases. So if you're working and the platform is down and it's Monday, it might really be because we're doing some stuff there. Our GPU machines have 12 CPUs and 80 gigs of RAM. That's roughly 3 times, maybe even 4 times what you have in a high-end gaming PC. And I really wish I had one of those at home to play the latest Battlefield. And finally, the cells. So I mentioned they're 900 megapixels at 30 centimeter spatial resolution. That's roughly the size of Zurich. So you can fit a lot of data in each of these cells. We pretty much optimize a lot of stuff there. But still, it happens that as you increase the area or as you increase the resolution, you pass that threshold, and we split the images into multiple cells. And with that, I'll hand it over back to Julien for some examples.
Cool. Yeah, thank you very much, Stefan. I think this is one last example I wanted to share because it also highlights both the iteration speed, but also the scale at which you can go with Picterra. So this is one example where a user detected slurry tanks across the whole country of Denmark. And I think what's very interesting about this project is that this took 2 weeks, so 2 calendar weeks, to basically do the whole thing. So from creating a detector, annotating the training data, testing it, measuring the accuracy, making sure it's good, and then running it at scale on the whole country. And in this case, they used some WMS aerial imagery at 25 centimeter GSD. And so it's quite a lot of data to process. I think it was close to 1 terabyte or a little bit more than 1 terabyte of imagery to crunch through. And so all of what Stefan explained with the cell splitting and so on, it was obviously used in this case. And again, it shows that you can train a detector and then apply it at scale with a single click without having to worry about any infrastructure or MLOps or whatever. We handle all of this for you, or Stefan and his team handles everything for you. Yeah, so we are nearing the end of the webinar. There is 3 main messages that I wanted to pass and to make sure that you understand them. So first, I think that using Picterra, what we are seeing with customers is that we help improve basically the success rate of machine learning projects, and this is mostly because by removing all of the infrastructure, the collaboration bottlenecks, all of this stuff, we basically allow your team to focus on what's important, and what's important for a machine learning project is understanding the use case, labeling creating some good training data, and then evaluating if the detector you built is actually answering the business case or the use case that you tackle. So really we allow a really fast experimentation and iteration phase, and it also enables our customers to discover more use case. So what we see very often is a customer starting with one very specific use case, and then they figure, yeah, okay, it took only a few days to train this detector, so I'm gonna try this other use case, and then they open a new line of business with another use case. So really, we are very keen on basically letting our customer go really wild in the use case that they choose and be very creative. And finally, I think the last one is we try to eliminate silos and foster collaboration. So we didn't cover this too much today, but we also have some collaboration feature. So if you have a team, you can share imagery detectors within your team. And we also have some exciting collaboration features coming up in the next few weeks or until the end of the year, which will allow even better collaboration. But really, we aim to be a bit the Google Docs of machine learning training, if you want. Yeah, before we close it, let me just go back to the detector that I trained at the very beginning. And let's see if I got results. Yeah, so okay, I got results. So you can tell I got results because you can see in the red testing area that I outlined before that I have some detection. So the green highlight here are the detection of the model in this testing area. So you can see it's actually working pretty well in this case. Granted, it's a bit of a limited evaluation for the model, but it's a really good starting point. And you can see that it also detected in the accuracy area that I have. And thanks to this detection, I actually have some score. So based on the detection that the model did in the accuracy area, I have some typical machine learning score. Yeah, precision recall and some measure of the shape accuracy, which is intersection over union for the one who knows a bit more. So yeah, this is just to prove that it took 15 minutes to train a machine learning model, and from here I could basically improve it further and add more images and make it more robust. Okay, so yeah, now we will look a bit at the questions that you sent on the chat during the webinar, and we'll address the hopefully all of them, but I don't know if we'll have time to address all of them. So let's jump into this. Let me look at the questions. So there is one question, which is around what's the reason for the 85% failure rate that I mentioned of ML projects. So if you look, like it looks in the industry, there is 90% of machine learning projects failing in the geospatial sector. And I mean, obviously I don't have all of the answer to this because I didn't do a study on this, but I think we have a few points that we can say. So I think one of them is, from what we've seen with customers, is just the difficulty of managing the data, the training data, the coordination with the annotation team. And then the machine learning team is very often overloaded with requests in most companies. So we have seen data science team that just push back on a project because they say, okay, we are booked for the next 6 months. And therefore, people just give up on getting the data science team involved. So by using Picterra, we also allow to kind of let the data science team focus on the most impactful things, and basically use us to make part of the process very streamlined and very easy. Another one is, what parameters of the model will you keep out of the hands of your users, customers, and which ones do you think make sense to pass them on? This is a super good question. I wish I had the answer to this. I think, yeah, I mean, to start with, I think it's something we are still discovering. So our goal is really to open up the parameters that are meaningful and that can make a difference, but that are also, let's say, understandable or intuitive. So obviously the users, if we open up the parameters, they need to kind of be able to make sense of it, to reason about it, to know how they should change the parameter to get better results. So I think we don't have a fixed set. So we are opening some parameters. I mean, right now, for example, we have 2 modes in the detector, so you can switch between counting and segmentation mode, which yeah, means we have detector doing both. You can also change the number of training steps, sometimes called epochs in machine learning. So there are already a few parameters that are open, but we are really willing to open more, and I think we'll basically learn this. And I think the other side of this question is, some of the parameters we want to find them automatically for users. So this is the goal of the experiment workbench feature that I was mentioning. There, the idea would be really that we search through the parameter space for users, and then we can also show to the users which parameters works better by just crunching through different set of parameters. Okay, we have another one. Hi, great job. Could you mix data from different type of imagery? So like SAR imagery or multispectral imagery. Yeah, this is a good one, and actually, yes, you can. So we have a feature that I didn't cover in the demo here, but that we call the multispectral. And so when you upload an image, you can choose basically to upload it as a multispectral image, and then the detector will use all of the spectral bands that are in your image. So basically, it's a way to either upload multispectral image. So if you have, for example, RGB and then the near infrared, which is something you see very commonly with drones or satellites, you can upload the 4 bands image, and the detector, the machine learning, will actually use the 4 bands of image. And in the UI, you can switch which bands are displayed, like you would do in QGIS or ArcGIS. And so this actually means that you can even upload some hyperspectral image. So if you have, I don't know, 50, 100, 150 bands, you can also work on this. Or you can also upload SAR data, because at the end of the day, SAR, I mean, it's a geospatial, you can represent it as a geospatial image. So you can definitely upload some SAR imagery on the platform and train your model on it. Another one regarding WMS. So when connecting to an imagery server such as WMS, are there any limits on the number of megapixels that can be loaded into the platform at once? So this is an interesting one. I think Stefan will have some nightmare story about WMS connection. I mean, the basic answer is no. Like on our side, we don't limit the amount of data we fetch from the WMS. What we have seen with customers, though, is that you need to make sure that the WMS server is beefy enough to handle the load. So if you ask us to fetch 2 terabytes of data from your WMS server, we will happily do it. But we've seen that some WMS server, they are not able to handle this load. But so in this case, we work with customers on benchmarking their server, making sure that it's yeah, it can handle the load that the platform will put on them. But yeah, no limits on our side. Just on the side of the server, it needs to be robust enough.
Yeah, and the connection needs to be robust as well.
Yeah.
Like, yeah, we will hammer your WMS with a lot of parallel queries at the same time. So better make sure it's stable.
Okay, another one. Do you have clients using your platform to analyze satellite imagery as well? Yes, of course. So yeah, actually, that's a good question because we mostly showed drone data and aerial data in the demo today, but we totally have clients using satellite imagery. So we have clients, I mean, you can use Sentinel-2 imagery, for example. You can even connect, for example, to Sentinel Hub, which has a WMS server. But we have a lot of clients also using commercial satellite imagery. So Planet, Airbus, Digital Globe. We've seen a wide variety of imagery. And also a few clients are using SAR imagery. So coming back to the question before, we have a few clients using radar satellite imagery. Okay, I think one interesting one, is your platform able to support multi-temporal data for training the model? This is a good question. I think there is two answers there. We don't directly support multi-temporal data, but you can work around this by basically stacking your data into bands. So you can stack your image of different dates in basically multiple bands. So I don't know if you have like 3 dates of a RGB image, you can stack all of this into a 9 bands image. And then the detector will use all of the bands. And we've seen with some users in the agricultural sector that the detector is actually able to figure out that it's multi-temporal data and to improve the results based on this. But we don't really, at least right now, have the direct support for the temporal aspect. There is one, if we have very large volumes of client data to be processed, for example, tens of terabytes of very high resolution optical satellite data, how can we transfer this to your system? Send us a hard drive. No, I think 2 ways. So first, you can one option would be to connect a WMS server. So if you have this imagery on your side hosted on a WMS server, you could connect the server. And then we have a feature called detection area where you can kind of limit the area of interest where you're running a detector. And so if you use detection area, we only fetch the data that's necessary. So we won't fetch the whole WMS data, but only the part that we really need. So that's a way to kind of be selective a bit about the data. Otherwise, I mean, you can also connect it. So we have an API, so you could automate the upload through the API. You can also upload from a URL. So if you have it on a blob store somewhere, you can upload. We can fetch it from a blob store. And finally, you can also, for example, upload it from Google Drive. So if you have all of this stored in Google Drive, you could import it through Google Drive. But I think in this case, the API might be the best. Yeah, API or WMS might be the best solution.
Yeah, and if you do this, shoot us an email beforehand so we can monitor this and and take a look at that.
Can you combine RGB images and DSM data and train detectors using both? Yes, you can, and we have seen people do that actually. So, and the way to do that is again the multispectral feature. So you would basically stack the 2 images in a 4-band image in this case, so RGB and then the DSM. And then you can upload this as a multispectral image on the platform, and then the detector will use both the optical data but also the height to detect your object of interest. Maybe let me look quickly at the time. Maybe a last one. Is it possible to export the trained model to be used for real-time detection, for example? Yeah, that's a good question. I think this is not really something that we focus on right now. So the model is built in such a way that it's really good on geospatial imagery. So it's really good on very large scale imagery. So you can, I mean, we have people uploading 200,000 by 200,000 pixels image and detecting on them. But there is always a bit of a trade-off in terms of engineering. So we are really good on very large images that you typically see in geospatial, but it means it might not be super well suited for real-time use case. So I think there the answer is unfortunately not really, at least not right now. But I mean, if you have some use case in mind, it would be interesting to follow up with us by email, and we can discuss a bit the specifics. Yeah, checking. Okay, could you offer custom development where I can use my data, geospatial or not? I guess, I mean, it's a bit of a difficult question to answer without knowing more, but we don't really offer custom development. That being said, I think you can, what we would at least push people to do is first test the platform with their data. So you can build your own model, you can build your training data set, and then you can see if the platform actually works for you. And then if it doesn't, we are very interested to have a look into why it doesn't work. And basically we try to not do too much custom development, but instead improve the whole platform so that it benefits all of our users. I think I'm just having a look at the question, but I think I covered everything. No, there is one. Do you provide different machine learning algorithms? As far as I know, different algorithms perform differently depending on the use case. Yeah, that's a very valid point. So I mean, we don't provide different algorithms. So what all of the platform is basically based on a CNN. I mean, it's our custom architecture that is based on a CNN. It's, let's say, based on the UNet. I mean, that was the initial architecture, the UNet for those who knows. And then we brought some ideas from other architecture like Mascar CNN. And YOLO. So we have our own architecture, and we really focus on it. So we don't provide other algorithms out of this. And I think at least right now, the reason is we want to get this one to be really good. And it's true that it might not work for all use cases, but for visual, let's say for optical imagery analysis, I think, yeah, CNN are a bit the state of the art. That being said, we provide, we will choose a backbone automatically. That's the best for your problem. So we are doing this automated architecture search. Something that I didn't mention is we are also thinking about a feature that we would call GPU blocks, which would be a way for basically users to run their own algorithm on the platform. So that's something that's not yet on our roadmap, but that we are thinking about. And so if you have some specific algorithms that you would like to run because you know they work better, yeah, shoot me an email. I would be interested to talk about it. I think that's it. Yeah. I think I covered all of the questions. If I missed one, I'm sorry, but yeah, thank you very much for all of the questions. And yeah, I think that's the end. We will follow up to all of the people who subscribed with a recording of the webinar, and we'll also include the slides, so you can have a look at the slides on your own. Yeah, so that's it. It was very nice to talk about machine learning to you, and I hope you had a great time. And if you have any questions, don't hesitate to follow up with us by email or by the chat that we have on the website. And yeah, Stefan, if you want to close it on your end.
It was a pleasure. Have a good evening or morning or afternoon, wherever you are.
Thank you. Thank you, everyone.
Goodbye, everyone.